Okay, dear students, so now we have in the previous video we have studied about transient current, the closing and opening of the inductive circuit and the growth of current in an LR circuit. Now this video we are going to see about the decay of current in LR circuit. See, when the circuit is broken, what will happen? The induced EMF, as we know that the induced EMF is equal to minus L into di by dt. That is again produced in the inductance, and it will slow down the rate of decay of current, which we have already mentioned. So we are going to study about the decay. See, when the circuit is broken, the induced EMF, that is minus L into di by dt, will be produced again in the inductance across L, and it slows down the rate of decay of current. So now we have the current value as maximum value. This is our circuit. See this one. Now we are having the maximum value I0 equal to E by R. Now what will happen? The current in the circuit will decrease from this maximum value I0. It will decrease from this maximum value I0 to 0. So during the decay, the current in the time t, now let us consider that at a time t, let current be I. In this case, E will be equal to 0. That is, EMF will be induced will be equal to, the EMF equation will be written using the Kirchhoff loop rule as 0 is equal to Ri plus L into di by dt. Previously, we have already written E is equal to I of R plus L into di by dt. Now, what is happening? We are going to take E is equal to 0. E is equal to 0 because there is a current, it is decaying from maximum value I0 to 0. It is decaying maximum value I0 to 0. When here it is 0, E will be also becoming 0. So, we are having 0 is equal to I of R plus L into di by dt. Now, we are just going to rearrange it. We are going to write it as di by I is equal to minus L by R into dt. We have used loop rule here, Kirchhoff loop rule, and we are going to rearrange the equation, and we, as usual, we are going to integrate it. On integrating, we will get log e to the base I is equal to minus R by L into t plus a constant c. So, when t equal to 0, I is equal to I0 or log of I0 equal to c. So, here we are going to substitute here, that is minus R by L into t plus log I0. We are again going to rearrange it, and we will get log e to the base I by I0 equal to minus R by, this we will take into LHS. So, I by I0 equal to minus R by L into t, or we can write I by I0 equal to e raised to minus R by L into t, or you will get it as I is equal to I0 e raised to minus R by L into t. I0 e raised to minus R by L into t. This is the decay current equation. And our growth equation was I is equal to I0 into 1 minus e raised to minus e raised to R by L into t. This was our growth of current in LR circuit. This is the decay of current in LR circuit. That is I is equal to I0 e raised to minus R by L into t. That is, at an instant time t, the current decay is shown. So, here also we can show the current decay using a graph. We are having current in the y-axis, and x-axis we are having a time t. Here we are having the current, and let this be equal to I0 equal to E by R, which is actually decreasing to 0, and let this be equal to L by R. This is 0, and this much is the time constant lambda. This is the time constant lambda. Here this is 0.65 I0. That is, when t is equal to That is, when t is equal to L by R, I is equal to I0 e raised to minus 1, or this is equal to 0.365 I0, or I is equal to 0.365 I0. Okay. Now similarly, you can put t is equal to 2L by R, you will get a value. T is equal to 3L by R, you will get a value. Therefore, we can say that the time constant L by R of a RL circuit can be defined as time taken by the current in the circuit to falls off to 1 by E of its maximum value when the external source of EMF is removed. That is, when capital E is equal to 0. That is the diagram shown here. Okay, this is 2L by R. You will get the corresponding value 3L by R, and it goes like that. This is the decay current graph time, or the rate of decay. The rate of decay of current. Rate of decay of current, that is di by dt is equal to minus R by L I0 e raised to minus R by L into t. That is equal to minus R by L into I. Okay. So it is clear that the greater the ratio R by L or smaller the time constant, more rapidly the current slows down or it will die away. And we are having the graph. This is the growth graph and this is the decay graph. This is the decay graph and this is the growth graph. Current in the y-axis and time in the x-axis. This is the growth and this is the decay time graph. Okay. Thank you.